Okay guys, let's take a look at today's lesson. What we're going to be working with today are tangent lines and derivatives. So we have talked about tangent lines before. We've actually done tangent line approximations before. We're going to continue that, and also finding derivative values. We're going to look at a couple of different things. So let's just kind of remind ourselves, we did work with average rate of change in the past. Can't remember which unit it was, but we did work with average rate of change, and this was the formula for average rate of change. That is the slope of the secant line. Just a reminder, you may have some questions that ask you for average rate of change. We're going to add to that our instantaneous rate of change, or derivative. We really have two different formulas up here. This one is called the definition of the derivative. That's the definition of the derivative, and this is the alternative form of the definition of the derivative. Two different forms to give you the same answer. It's kind of whatever your preference is. So in this particular case, what we're doing here is we're actually using these equations, these limits, to find the derivative at a particular location, at a point. This isn't going, these two formulas particularly aren't going to give us the equation of the tangent line. They're going to give us the value. They're not going to give us the equation of our derivative. They're going to give you one value in the derivative. They're like a single use formula. And we would use these. They're easier to use than the ones with the x's in them. They're easier because they have numbers in them. But they will only give you one value of the derivative. Just the value that you're particularly looking for. The value when x is a. It's going to give you that value. So, you know, I kind of prefer this one, but it really doesn't matter. You could use either one. So there are several things that we use the derivative for. One that we'll be using today is f prime of a, so say f prime of 2. You know, what's the derivative value at 2? Is basically the slope of the tangent line to the function at 2. Right, so for example, if we had like a parabola, let's just look at the parent parabola, and let's say that I wanted to find equation of the tangent line at, say, 1. You know, I'm looking for this. So the value that I get out of this equation is going to give me the slope of this line. That's what it's going to give me. That's what this is telling us. That f prime of a is the slope of this tangent line at a. We'll just call that a. Okay, so that's what it's going to find for us, the slope of the tangent line. Another use for the derivative at a location is basically the instantaneous rate of change of y with respect to x. So that sounds really like abstract. What in the world does that mean? We really like to bring context into that rather than just it's the instantaneous rate of change of y with respect to x at x equals a. One of the contexts we use is velocity. F prime of a is the instantaneous velocity when, S is our displacement. That's just the normal letter that we use for a position function. S, like V, is the normal letter that we use for velocity function. S is the normal one that we use for displacement or position. When our variable x is actually a t for time, and you would have dealt with these like in physics. You probably had lots of physics problems like that, where you're dealing with velocity and time and that kinds of thing. All right, so those are just some of the main uses of the derivative. The ones that we're going to be using today are these, where we're going to do slope with tangent lines and instantaneous velocity. So just as a reminder, we've done linear approximation lots of times. Okay, a lot of times this year. This is I guess the last time that we're going to be doing it this year in preparation for next year. In fact, the test that I just finished giving the BC Calculus students had a linear approximation problem on it. And not everyone got it right. What? What? We're just doing a tangent line, right? It's a tangent line. That's not hard. And we're using it to approximate a value. That's all we're doing. So for example, if I wanted to approximate a value on the parabola, usually we don't do it with a function that simple, but let's just kind of go with my thinking here. If I wanted to approximate a value on the parabola, I could use these y values of the tangent line to do so. right? That's what a tangent line approximation is. It's using the y values on a tangent line to approximate the function value. Typically, I mean, you can see the closer I am to the point of tangency, the better approximation I would have, right? If I try to approximate this value using this value, it's not going to be that great, right? If I try to approximate this y value using this y value, that's not a good approximation. But if I'm close to the point of tangency, it would be a good approximation. That's what we use them for. That's what this linear approximation is using the tangent line to approximate a value on a function, a really complex function usually, one that we wouldn't be able to do by hand on our own. So that's the benefit of it. So let's go through the process, remind you the process. When we want to find a tangent line, what we do is we first need the point of tangency, right? The point when the line touches the graph of the function. In this case, it would be this point right here. We need to find that. Usually it's given to us, or at least the x value is given to us. If we just have the x value, how would we find the y value of that point? Just plug it in, right? Plug it into the function. I mean, that's not too bad. So the next thing that we do is we find the slope, m, by finding the value of the derivative at that point of tangency. That's what we're going to be working on today, finding the value of the derivatives at the point of tangency. And then we get to substitute in one of actually it is my favorite equation of the line. I love this equation of the line. Y minus y1 equals m times x minus x1. This is magnificent, right? Because these two, that's our point of tangency. x1, y1 are the point of tangency. This value is our derivative value at the point. Okay, so those are the three things we need to write the tangent line. The point of tangency and the value of the derivative at that point. And then we can use that to do a linear approximation. Okay. Questions on just the abstract concepts so far? We have a few examples on the back. Okay, let's go to our examples. Okay. So let's talk about finding derivatives just in general. If you have a non-polynomial, I'm going to want you to use the definition of the derivative. And we're just going to practice it. Okay, we're just going to practice it. Because next year you're going to learn a lot of different derivative rules for a lot of different kinds of functions, right? There's a whole, mess of derivative rules that you will learn. But the definition of the derivative works for everything. And so I'm not going to teach you all of the derivative rules this year. I want you to practice the definition of the derivative. Okay, but we will, when we have a polynomial, we will use a derivative rule called the power rule. And some of you may remember the power rule, some of you may not. I will review it before we do a polynomial. So those are your two options. If it's a polynomial, we can use the power rule, which is just a rule. It's quick and simple. If it's anything else, we're going to use the limit, the definition of the derivative. Okay? So in this case, we're wanting the equation of the tangent line. We need the derivative value at 1, and then we need the point of tangency, which, the x value is 1. So we need those two things to be able to write the tangent line. All right. So let's just write out my favorite equation of the line. Y minus y1 equals m times x minus x1. Okay, I already have x1. It's 1. I don't have m yet. I'm going to have to find that. I need y1. How am I going to find y1? I'm just going to substitute that in, right? Just sub that in. So the square root of 1 plus 3 is the square root of 4, which is 2. So this is just y minus 2. Okay, is everybody okay so far? I just have the point of tangency. This is my point of tangency. 1, 2. Okay? So what we do with the radicals is we just take the principal value of the radicals. Plus minus would include another value, not the principal value. So it's just as if we would put it in the calculator. The calculator would generate principal values. That's all we're doing is we would generate a principal value, which would be the positive root 2. All right, so to find m, it's a little bit more complex. We're going to have to use the definition of the derivative. I'm going to write it up here for you so that you can see how I am substituting into it. You don't have to memorize this. I'm going to give you the formulas each time, so you don't have to memorize it yet. You will, but not yet. So the limit as, we're going to use, actually I'm going to use the second one. The limit as h approaches 0, I'm going to use the actual definition of the derivative. The limit as h approaches 0 of f of a plus h minus f of a over h. Okay, so this is the formula that I'm going to use. Could you use the other formula? Yes. I'm not going to. I'm going to use this one. Okay. So, I'm just going to work down here. We're going to do the derivative work down here. So what I'm going to do is I'm going to take this, the square root of x plus 3, and I'm going to put it inside this formula. It's important for us to know what a is. Okay, we need to know what a is before we start plugging in. A, in this particular instance, is 1. A is the x value. Okay, so a is the x value. Everywhere there's an a, I'm going to put a 1. So this first piece, so we have the limit as h approaches 0. Okay, this first piece, f of a plus h, wherever there's an x in my function, I'm going to put 1 plus h. 1 is my a. So I'm going to write, in place of the x, 1 plus h, and then I'm just going to copy the rest of the stuff, plus 3. That gives me this portion. Okay, I've just done the f of a plus h portion. Minus, then f of a. So that means I'm going to take this number and plug in for x. So 1 plus 3, all over h. Okay, so my first step is simply substituting into that formula. How are we doing with that? Any questions on that? I know it's kind of weird because it's like you're kind of substituting this into the formula or this into that. I mean, it's just kind of a weird kind of thing. Students really get confused with this formula. But if you kind of keep in mind, so I'm just going to highlight this part. If you keep in mind that this f of a plus h, that's taking this function and putting where the x is, a plus h. That's what I did right here. Okay, that's what that is. And then minus f of a. So I'm going to take my function again, and I'm going to plug an a into it, which is 1. All right. Okay. So let's clean it up just a little bit. So that's the limit as h goes to 0. Notice I'm bringing my limit along. Poor little thing. It doesn't want to be left behind. So this is the square root of 4 plus h minus, so this is square root of 4, right, which is 2, all over h. Okay, is everybody okay with that? So let's think about the limit laws that are, and all the limit rules that we looked at yesterday. What would be a promising way to work this? The conjugate. The conjugate would be a promising way to work this. So that's what we're going to do. We're going to multiply this by the conjugate. So the square root of 4 plus h plus 2 over square root of 4 plus h plus 2. Okay, so we have the limit as h goes to 0. So remember the beauty of the conjugate, and that is that the inside and outside terms net out to nothing, right? That's the great thing about the conjugate. So all I have to worry about is multiplying the first terms together. Root 4 plus h times root 4 plus h is 4 plus h. And then I have to worry about multiplying the last terms together. Negative 2 times a positive 2 is a negative 4, all over. Now remember, don't distribute in the denominator. You'll miss the magic. You could miss the magic. Don't do it. So h times, we're just going to write square root of 4 plus h plus 2. Okay. So we can see in the numerator, right, those 4's are going to go away, and I'm just left with an h. So this is the limit as h goes to 0 of h over h times square root of 4 plus h plus 2. And there we go. The h's go away. That's a beautiful thing. So now I substitute the h in, the h of 0. I'll put 0 where h is. So I get 1 over the square root of 4 plus 2, right? Because that h becomes a 0. 4 plus 0 is 4. And we know square root of 4 is 2, so this becomes 1 over 2 plus 2, or 1 over 4. That's my slope. That's what goes right here. This is the equation of my tangent line. Okay? Once I find the equation of my tangent line, I'm asked to use it to approximate y of 1.2. Okay, so we're going to use this tangent line to approximate. Let's kind of carve out a little bit of space right here. We'll just write it right in here. So I'm going to put a 1.2, I'm going to substitute that in for x. And I'm actually going to solve, I'm going to move the 2 over just for convenience. So I'm solving for y, right? So I'm going to add the 2 over. So y equals 2 plus 1/4 times 1.2 minus 1. Okay, so this is my part B. I'm using the tangent line to approximate 1.2. Because see, if I put a 1.2 in here, that's not going to help me any, right? What is the square root of 4.2? I mean, I don't know. We could estimate it, right? But that's why a benefit of the tangent line. I can find an estimate pretty easily, actually, just using the tangent line. So let's keep going. So I have 2 plus 1/4. So we know that 1.2 minus 1 is 0.2. And I really don't like mixing decimals and fractions. I really don't like that. So I'm going to turn 0.2 into a fraction. Right? 0.2 is 2/10, which is 1/5. So I'm going to make that 1/5. So y equals 2 plus 1/20, which is 2 and 1/20. Now mixed numbers are not my favorite thing, but in this case it's pretty easy just to leave it as a mixed number. If you want to make it improper, you certainly can, or you can leave it as a mixed number. It's totally up to you. So this would be an approximation of the square root of 4.2. That's probably a pretty good approximation. I know we could check it out on our calculator, but it's probably pretty good. Because 1.2 is fairly close to 1, right, on the tangent line. That's pretty close. It's not like the one I showed you with the parabola where it was really far away. Right, that should be pretty close, as close to the point of tangency. All right, questions on that first one? Okay, so that leads us to the second one, and the second one we have a polynomial. So I'm going to remind you how to do the power rule. Some of us I know remember, and some of us may not, so I'm just going to remind you. So let's say we have f of x equals x to the n. Okay, if I want to use the power rule, this is how the power rule works. F prime of x, I bring the exponent, that number, in front, and then I subtract 1. That's the power rule. It works just with polynomials. Doesn't work with everything, just polynomials. Okay, so that's the power rule. And another thing that we need to know is that the derivative of a constant is 0. So like the derivative of 3,000 is 0. That's just something to memorize. It's really not an easy way for me to show you that. So our scenario is we have an object being dropped from a height of 3,000 feet. Its distance above the ground in feet after t seconds is given by, and here's our equation for distance. Find the object's instantaneous velocity after 4 seconds. So let's talk about velocity for just a moment. Velocity and speed are different. You may know that from physics already if you've had physics. So velocity has magnitude and direction, and speed is just magnitude, right? It's just magnitude. Like on your speedometer. Your speedometer, well, cool speedometers nowadays do have north, south, east, west on them. Okay, but I mean just the regular numbers, right? If you're going like 20 miles an hour, you're going 20 miles an hour. I mean, you're not going left, right, up, down. I mean, you're going 20 miles an hour. That's speed. So this velocity information is going to be important to us. It's going to give us direction as well. All right, so let's first find our derivative. We know we get instantaneous velocity from the derivative of the position. Okay, so I need to take the derivative. So h prime of t equals. So the derivative of 3,000 is 0. Now, let's not get that confused with the 16. The derivative of 16 is not 0. 16 is not by itself. It's attached to something. That's a different rule. There's so many different derivative rules. Why? So I'm only doing a couple. Okay, so this little 3,000 is off by itself. It's kind of poor little thing, all vulnerable by itself. The derivative just erases it. It's like, oh, see ya. It's gone. So the derivative of 3,000 is 0. This one we're going to use the power rule on. Right? So I have a 2. I'm following the power rule. I have a negative 16 times 2, bringing the 2 down, t to the 2 minus 1. And I'm just writing it all out so that we can see the power rule. You don't have to write all this. I'm just want to make sure we're clear. So what do? I bring the 2 down front. I'm going to have to multiply it by whatever's down there. And then I subtract 1 from the exponent. So my derivative is going to be, what is that, negative 32t. That's my derivative. I'm going to use the derivative to find the instantaneous velocity after 4 seconds. Because that's what the derivative of a position does. It's the velocity. It finds us velocity. So h prime of 4 is negative 32 times 4, or what is that? Negative 128. Now this is in context. Like it or not, I guess as a mathematician, I'm not extremely fond of units. I know your science teacher will be very upset with me, but I'm not extremely fond of units, but they're there, and when they're there, we have to use them. We don't really have a choice. We have units. This is in feet and seconds. Okay, we have to use them. So there's 2 different ways we can write the answer to this. All right, so I'm helping you. We're transitioning into calculus because you have to write just a sentence or 2 in calculus to describe what's going on. So we could say that the height is decreasing at 128 feet per second. That's possible. We could say that. Notice how I used the word decreasing. That took the place of the negative. Right? I don't say decreasing and a negative. Because let's talk about what this velocity is telling us. It's giving us a direction. Right? A negative velocity. In this circumstance, we're dropping something from a height. So negative velocity means that we're traveling down. Right? So this is traveling down, or the height is decreasing. So this is one way we could write our answer. Another way we could write it is height is changing at negative 128 feet per second. That's another acceptable way. You just really need to kind of find what makes most sense to you and stick with it. Both of them are equally correct. Okay? So the height is changing at negative 128 feet per second, really technically at t equals 4 seconds. Okay? How is that? Any questions?